Okay, so let's start this. Yeah, that's good if you can stay close. Okay, so now we are going to look at a method called conjugate beam method. I mean, you might be wondering, like, why we learn so many methods to calculate deflection. I can use a simple computer program which can, of course, derive deflection. The reason is any computer program gives an output for your input. Because if your input is wrong, your output will be wrong. Okay, so it is like so if you give the right input, you can get the right results. So to give the right input and to understand how to define the parameters and how to approach a problem, you need to thoroughly understand the theory, how it works. So, I mean, when you work out these problems, you define support conditions, you define E values, I values, and very often a lot of people make a mistake in exams that when you define a I value in a wrong units, then you will get a wrong results. So sometimes you will get a deflection like 50-meter deflection. So 50-meter deflection is like about the height of this building. Okay, so that is not possible. So that is why we are doing so many. This is just practicing our brain to adapt. So one of these method is called conjugate beam method. Conjugate means it's reciprocal. So we have a beam and we'll have a reciprocal of the beam in a different system, and we will see how to use this to derive deflection and slope. So the conjugate beam method, developed by Otto Moore in 1868, generally provides a more convenient means of computing slopes and deflections of beams than moment area method. So last week and in the morning, we have seen how to do a problem using moment area method. We know there are some difficulties. Means it's a bit complex. It's not straightforward. So you need to have a thorough understanding of how deflection is occurring in a beam. Then only you can indirectly find the deflections and slopes. Although the amount of computational effort required by the two methods is essentially the same. The conjugate beam method is preferred by many engineers because of its systematic sign convention and straightforward application, which does not require sketching the elastic curve of the structure. So you might have seen that sketching the elastic curve of the structure is necessary for moment area method. And also sign convention wise, we don't have much clarity on the sign convention. The conjugate beam method is based on analogy between the relationship among load, shear, and bending moment and the relationship among M over EI, slope, and deflection. Now let's look at this. You are familiar with these equations. That is, first derivative of the shear force is equal to the load acting on it. First derivative of the bending moment is equal to shear force. So means second derivative from this we can derive second derivative of bending moment is equal to load. And you have also seen this d theta over dx is equal to m over ei. We have seen this while deriving the simple beam bending equations. And dy by dx, you know this, and d2y by dx squared m over ei, you are familiar with this. We use this for direct integration method. Do you see a similarity between these two? Say between these two, any similarity? So here instead of shear force, we have slope here. Here instead of bending moment, we have deflection here. Instead of bending moment, we have deflection here. So it looks similar. So, for example, if you apply a load on a beam, you get shear force and bending moment. If you apply a load on a beam, you get shear force and bending moment. So that is what here we get. First derivative of the shear force is load. Suppose if we apply M over EI as the load on a beam, say you get M over EI diagram, right? So if you assume that diagram as a load, so that shape of the diagram as a load. If you apply M over EI diagram as a load on a beam, then the shear force is equal to, so if you apply M over EI diagram as a load on a beam, then shear force of that beam is equal to, what is that? Slope. So if you apply M over EI diagram as a load on a beam, the slope is equal to the shear force that you derive on that beam. For the M over EI diagram, M over EI load, if you derive a shear force, that shear force is equal to the slope of the actual beam. Similarly, if you apply M over EI as a load on a beam, so say M over EI, so you normally get like, we get a M over EI diagram, something like this. Okay, so this is, say earlier we had 37.5 over EI, 37.5 over EI. So if we apply this as a load on the beam, so if this is the shape of the load, if the load is distributed like this on a beam, then if you derive shear force to this load on this beam, that is equal to slope on a real beam. Okay, because what we get here as a shear force is slope. What we get here as a bending moment is deflection. So if you apply M over E as a load, Then the bending moment you get on this beam at any point is equal to the deflection of the real beam. Okay, so there is a reciprocal, like you apply a load and then you do, due to load you get a bending moment diagram, then you convert that into MOVEI diagram and apply that as a load on a reciprocal beam. So in that reciprocal beam, the shear force and bending moment you derive on the reciprocal beam is equal to slope and deflection of the real beam. Okay, so when we do a problem, you'll see it. Okay, so this is what, in other words, if you assume MOEI as a load on a beam, the shear force of the conjugate beam at any point will give you the slope of the actual beam. And the bending moment of the conjugate beam will give you the deflection of the real beam. So if you derive bending MOEI diagram or plot MOEI diagram and apply it as a load on a beam, the same beam, you can simply derive shear force and bending moment at any point, and that's the slope and deflection at that point. Very easy. Although it takes considerable time, equal to what we take for moment area method, what you get is a straight answer. Okay. And when you convert a real beam to a conjugate beam, this is what we need to look at it. Okay. So if you take a real beam, it has a pin. If it has a spin support, what can you say about slope and deflection of that pin support? At a pin support, you can have a slope, but you cannot have a deflection. Okay, you can have a slope, you cannot have a deflection. Now, that beam is going to be converted to a conjugate beam. So in the conjugate beam, what is slope equivalent? Shear force. What is deflection equivalent? Bending moment. So a pin support in a conjugate beam, a pin support in a real beam, when you convert it as a conjugate beam, at that location, at that point, so this shear force and moment are going to be slope and deflection. So in a simple support beam, you can have slope. So means in a conjugate beam, you can have shear force. In a real beam, you cannot have deflection. That means in a conjugate beam, you cannot have, you cannot have moment. So what kind of a support can give you no moment but shear force? A pin support will give you, at a pin support, you can have shear force, but you cannot have moment because it will rotate. So a pin support will become a pin support in a conjugate beam. A fixed support is what very interesting. If you take a fixed support, no slope, no deflection. So that means no shear force, no bending moment, means it should be a free end. Because if you have any sort of support, there will be at least shear force. So it should be a free end. So fixed support will become free end in the real beam, in a conjugate beam. A free end in the real beam will become fixed support in a conjugate beam, because in a free end in a real beam means there will be slope, there will be deflection. So if you need to have both shear force and moment in a support, that support should be a fixed support. Okay, only fixed support can carry moment. Then internal pin will become internal hinge. An internal hinge in a real beam will become internal pin. So that is the only difference. So when you look at a real beam, and once you work out the bending moment diagram, then you are ready to convert to conjugate beam. Then what you should do, you should convert the supports first, then apply MOVA as a load, then you find shear force and bending moment at any point you want. Okay. The sign convention. So if the positive ordinates of MOVA diagram are applied on the conjugate beam, it is applied as a load upward. Okay. So upward loads in positive y direction and vice versa. If it is on the negative side of the, if say for example in this case, here positive moment M over here. So the load is now here is going to be upward. If it is on the negative, it will be downward. Okay, so when you convert the MOA as a load, if it is on the positive side, it will be an upward load. If it is on the negative side, it will be a downward load. Okay. Then the positive shear in the conjugate beam denotes a positive slope, clockwise slope, counterclockwise slope of the real beam. The positive bending moment in the conjugate beam denotes positive, that is upward deflection in the real beam. Okay, so whatever you derive, if it is positive slope, it is counterclockwise rotation. So positive bending moment, it is a upward deflection, positive deflection. So let us see some examples how we convert a real beam to conjugate beam. If you look at the pin, it becomes pin, roller becomes roller. If this is a fixed, becomes free, free becomes fixed. Here it's a free end, become fixed. Internal roller, hinge. External pin or outside edge pin becomes edge pin. Fixed, free, internal hinge, internal pin, external roller, external roller. So the external roller and pin doesn't change. So if you look at this case, this won't change, this won't change. This hinge will become a roller. This roller will become a hinge. Here it's a fixed, becomes free. Here it's a roller, it is the roller. Fixed, free, fixed, free. So if both ends are fixed, okay, so you have a beam where there's no support. Okay, so if both ends are fixed, that means what? Huh? If both ends are fixed, what kind of a structure it is? It's statically indeterminate. So we are no longer discussing about statically. Similar statically indeterminate you can see here. A prop cantilever. So fixed becomes free. A roller. Can you support the beam in just a roller support? So it is like the current Sri Lankan government. Okay, sitting on a roller support. Anytime it will collapse. No time it will collapse. Unless there's an upward wind is acting on it, so self-weight it can sustain. That's also not possible, just for a joke. So this is statically indeterminate. So we don't need to worry about statically indeterminate because statically indeterminate is not within the scope. So here you have a pin, internal rollers become internal hinge, external roller become external roller. So that's how we convert the real beam to a conjugate beam. Before we go to this problem, okay, I'm going to look at the one that we have done in the morning. Okay, so in the morning, we did this example. Conjugate beam problems. So now we got a bending moment diagram, right, already. So I can skip that step. MOIA diagram, right? This is 37.5, right? Minus 37.5 over EI. Correct? Okay. Now let us convert. So this step anyway, you are experts. You know, finding bending moment diagram. You are experts. So I'm not going to spend time on deriving bending moment diagram. Sometimes we have to spend time on it, but it's okay. So now, since we have the bending moment diagram, I'm going to plot this conjugate beam. So can you help me to plot the conjugate beam? So this is a fixed support. It becomes free. So this is a free point. Internal hinge. Internal hinge becomes internal pin or roller. So internal pin. This one, external roller, remains external. So this is a conjugate beam. Now I need to apply MOIA as a load on this. So what is MOIA diagram? This is my MOIA diagram. Okay, this is my MOIA diagram. 37.5 over EI. Here I'm not going to mark any negative or positive, because if it is on the below that curve, it's going to be acting down. Okay, so only values. So now the load is acting like this. For the negative M over EI, load acting downward, positive load acting upward. Okay. So this is the conjugate beam with the load applied on it. Now in this beam, you just see freshly this sort of loading. Any point you take, there the shear force and bending moment for this load is equal to slope and deflection in the real beam. So now we were interested, we were finding this deflection at C, right? This is A, B, C, D. We were finding deflection at C, right? Now for this setup, I need to find these reactions. RB. RD. Can you find me the reactions RB and RD? So you have to do the same thing, balance vertically upward, and balance all the forces horizontally and take moment. So if you consider this applied upward RB plus RD plus the load on the upper side, that is half times 6 times 37.5 over EI minus half times 3 times 37.5 over EI is equal to 0. So RB plus RD is equal to minus this is 37.5 minus 56.25. Okay, so that is the RA plus RD. If you balance horizontally, you can find HB to be 0. Then take moment by B. You can find RD into 6 plus half into 6 into 5 over EI, and that is the load acting upward, and the center is at the middle, 3. So into 3, that is counterclockwise, again another counterclockwise, plus half into EI into 3. So this is also counterclockwise, this load. So this is acting to take moment by B, so that is also counterclockwise. So that is at about 2 meters. The center is at 2 meters. Is equal to 0. So if I remove 6 from this, 6 goes, 6 goes, 2 and 3, 6 goes. So RD is equal to 37.5 into 3 divided by 2, that is minus 56.25 over EI minus 37.5 over 2. Minus 18.75. 75. So RB is equal to 25 EI. This is minus, so minus will become plus, plus. So 18.75. So these are the two reactions. RB has a positive reaction and RD has a negative reaction of minus 75 over EI. So in the previous example, we were interested in finding the deflection at C. So that is the point C here. So if I cut the conjugate beam here, then I can expose the bending moment and shear force, right? I can expose the bending moment and shear force. So now let me draw this section which I have cut. Here it is 18.75 over EI. Here the load is upward. Here the load is downward. Now this is shear force V and this is moment A. The reason I took on this side because to keep in my sign convention. Otherwise I had to go to the other side and my entire sign convention will flip it. Okay, prevent that sort of a catastrophe. I have to keep on this side. Just imagine even a simple bending moment diagram, we need to be very careful. Say, you can take the other side of the beam, but I took this side of the beam. So just imagine that in a big country where here the what will happen maximum, we'll get a wrong with the plus sign convention, but we'll get the same answer. So even for a sign convention, you got to think about it. But the people who rule the country, they make a big decision, but they don't think. That's why in the future, you have to choose an engineer to run the country. I don't, or maybe someone who can logically think, okay, engineer means it will lead to some other example, okay. So now let us take moment. If the moment at this point should give me the deflection in the real beam and the shear force should give me the slope in the real beam. So now let's take, so this is at about 6 meters. So at 6, if I take moment M, so that M is, but I'm taking moment at this point, okay? So M is counterclockwise. When I take moment at that point, the upward load is going to have a clockwise moment, and downward load is going to have a counterclockwise moment. Okay? So the moment due to upward load is going to be clockwise, so that's minus half into 37.5 over EI into the distance is 3 and the distance to the centroid from here is 1. And the reaction is going to be again clockwise. So minus 18.75 over EI into 3 plus half into 37.5 over EI into 3 into the distance to the centroid of the downward load is 3 plus 2, 5. Okay, that should be equal to 0 because at any point net moment is 0. Okay, any point. So M is equal to then, so 37.5 into 3 by 2, that is 56.25 over EI plus 18.75 into 3, another 56.25 over EI. That is from this part, previous part, minus 37.5 3 into 5, 2. 37.5 into 3 into 5 is 562.5 divided by 2. That is minus 281.25 over. That is 56.25 plus minus minus 168.75 over EI. Okay. Did we make any mistake anywhere? M is correct. Half 37.5 over EI into 3 is the area into 1. Correct. Minus 18.75 into 3 and plus half 37.5 over EI into 3 into 5. So okay, so 168.75 over EI. So this is the moment at this point. So that should be equal to the deflection in a real beam. So let us see whether we have done it correctly previously. What is the deflection we got? We got delta CS 168.75 EI when we did using moment area method. But we didn't have any idea because we know we have sketched it. We know it is downward and we got a value, and that value we know, okay, that is a deflection, but it is downward because we have sketched it. Okay, because we know it is downward because we assume this is our elastic curve, deformed curve. But here what happens is it tells you minus 168.75 EI. It tells you that, look, the deflection is downward because it is minus. If you get a positive value, that means the deflection will be upward. Okay, so that is the beauty of mathematics. So that is why this method is preferred. Now, we didn't do much of a sketching and finding incorrectly. We straight away, we found the value. That is the advantage of using conjugate beam method. Now, if I find, therefore, the deflection in the real beam at C is equal to minus 168.75 over EI. So the bending moment in the conjugate beam is equal to the deflection in the real beam. Now we can find even slope as well. So if you ask me what is the slope, that is shear force. So what is the shear force at 6? At 6, if you balance all the forces upward, you have minus V. You have minus V, which is acting downward, and you have minus half into 37.5 over EI 3. Then you have plus 18.75 over EI minus half into 37.5 over EI. So I'm making a mistake here because now I'm acting everything upward. So V is correct, minus V, but the load due to this one is plus. It's acting upward. Okay. Then the vertical reaction is plus. Then this is minus. That is correct. That is equal to 0. So V is equal to now. So this will cancel off. Same value. So it is 18.75 over. That is, if you substitute the values now, you have to be very, very, very careful that when it comes to E, it should be in E should be in kilonewton per meter squared. I should be in meter to the power 4. Otherwise, you will get a very wrong answer. Because load is in kilonewton, length is in meter, so our calculation is kilonewton and meter. So when you substitute E, it should be kilonewton per meter squared. I should be meter to the 4. And this V is giving us a positive value, 18.75 over EI. That means the slope is counterclockwise. Slope is counterclockwise, considering the undeformed axis of the beam. That's why I told you earlier in the morning, we can't assume slope to be 0 at C. Because in the morning, we had a temptation to, or tendency to assume the slope 0 at this point. It is not 0. It is something else. There's a positive slope. So that means the maximum deflection is somewhere here. So delta C is not the maximum deflection. Maximum deflection is between B and C. Because the slope is on the counterclockwise direction at C. So that means it was clockwise and then have 0 and then going up. So that's why we need to be very cautious. So this just to compare the two methods, and now you might understand this better. I think now you might get a better picture of conjugate beam method, how to transform support conditions, how to transform M over E as a load. Okay. So now let us take an example. So this is what something similar to this we have done now. Let's take this. Okay. Now, if I substitute the correct value, say if I take this value, let us try this as well. If E is this value, normally if it is given like this, if then the deflection at C minus 168.75 over EI, right? So I need to substitute E and I. So E is 200 gigapascal. That is 200 into 10 to the 9 Newton per meter square. So if I take this one, it should be 200 into 10 to the 3, so 10 to the 6 kilonewton per meter square. Okay, I take 1000 for kilonewton. So now I can substitute this. I is 70 into 10 to the 6 millimeter to the 4. So 1 millimeter is how many meter? 1 over 1000. So that is 10 to the minus 3. So that should be 70 into 10 to the 6 into 10 to the minus 12 meter to the 4. So if I substitute this value here, 75, 200 into 10 to the 6 times 70 into 10 to the minus 6, because 10 to the 6 and 10 to the minus 12, yeah, 6 will cancel out, so minus. So now this minus will also cancel off. Value I'm getting is 168.75 divided by 200 divided by 70. That is minus 0.01205 meter. Okay, you need to be very careful. It's meter. So that is equal to how many millimeter? Minus 12.05 millimeter. So that is the deflection at C in millimeters. Suppose if you substitute the wrong value, you get some 120 meters displacement. 100 or maybe 2-3 zeros, it will be 100 meters, 12 meters. So 12, one floor to floor height of a building is about 3.5 meters. So 35 meters means 10-story building. Okay, so we need to be very careful about these measurements. So let us take the second example. Determine the slope and displacement at C of the beam. Use conjugate beam method. So first step is plotting the bending moment diagram. For any problem, plotting the bending moment diagram. So can you plot the bending moment diagram first? So if you plot, I think you might get something like this. Correct? 6 kilonewton meter, 12. Correct? So that is the bending moment diagram for this beam. So now we need to convert this to a conjugate beam. So we are going to convert it to a conjugate beam. A pin is going to be a pin externally. An internal roller is going to be a hinge here. And the free end is going to be a fixed end. So that is the conjugate beam. This becomes the end pin, this end pin. Internal roller becomes hinge, free end becomes fixed. Okay. So now we need to apply that load on this beam. Okay, so we are going to apply this load on this beam. So So we know that when you have a load on the upper side, the load, when you have the MOIA on the upper side, the load acting like that. This is 6 over EI, 12 over EI. So this is the new beam, new conjugate beam constructed by us using the reciprocal of the support condition and the load. So now we need to find the reaction, support reaction in this conjugate beam. Because we are interested in finding the displacement at C. The issue is this beam has a hinge there. Okay, this has a hinge there. So hinge means, you remember, earlier also we had that hinge. Say you have a cantilever and they have another beam. So this beam transfers the load on the cantilever. So BA component of the conjugate beam is going to transfer the load at B to the cantilever BC. So the BC is going to be a cantilever. So now we need to take this part. We can break this into two. So here we have RA, HA, here we have RB. So that RB is going to be a load here, RB plus okay. So here there is a RC, MC, so without finding RB, we can't solve the other side, because other side has its own load, but then there's the RB acting on that one. So we need to find RB first. Okay, so what is RB? How to find RB? It's very simple. Only the complex part is the load, but otherwise it's simple. So if you look at this one, 6 over EI, 12 over EI. So when you consider RA plus RB plus the load on this side, half times 6 over EI into the distance is what is interesting. Here it is 3, but here, since this is 6 and this is 12, this is going to be 2 and 3. 2 and 1. Half 6 over EI into 3. That is the upward load, plus another upward is half into 6 over EI into 1, that is the small component on this side, minus half into 12 over EI into 2 is 0. Okay. So RA plus RB is equal to, this is 9, this is 3, 12. So 9 plus 3 is 12, and here minus 12 is 0. So RA is equal to R minus RB. So RA is equal to minus RB. So if you take moment by A, RB into the distance to RB is 6. RB into 6 minus, so RB into 6 is, RB is acting upward, so it's counterclockwise, RB into 6. Then this load is also acting upward, so that is plus half into 6 over EI into 3, and that load, I mean this, I'll shade this in 2 colors. I don't know whether you can see the colors. So one is this part, other one is the small part. Okay. 3, the distance to that is 2 meters. So that is the moment. Half 6 over here into 3 is the area, the distance 2, plus half 6 over EI into the base is 1, so that's the area, and the distance is 3 plus 1/3. Okay, so 3 is to the edge of that point, and then in that 1 meter, the distance to centroid is 1/3 of that 1 meter. So that is 3 plus 1/3. Okay, so 3 plus 1/3 is 10 over 3. Then this is counterclockwise, then this is clockwise, minus half into 12 over EI into 2 meters, and the distance to that is that 3, 4, and then 2/3 of the 2. Okay, 2/3 of the 2. So 2/3 of the 2 is 4 over 3. So 4 over 3 plus 4. Okay, 4 over 3 plus 4. That is 16 over 3. Okay, that is 16 over 3. That is equal to 0. So if you remove 6 goes here, goes there, goes there, here 2. Then this 2 and 2 cancels off. This 2 will cancel this to 5. So RB is equal to, so this one is now 2 into 16 over 3. So that is 32 over 3 EI minus 3 over EI minus 5 over 3 EI. So that is, if you put everything on the common base, 3 EI, 32 minus 9 minus 5. So that is 32 minus 14. That is 18. So 18 over 3 EI. That is 6 over EI. Then RA is minus 6 over EI. Okay. So we found the reaction. Now this reaction will act as a load on the other part. Okay. So if you look at the components, so if you take this BC component, so the BC component C B, it already has a load. The load is 12 over EI, and an additional RB. RB is 6 over EI. Now here there will be a reaction RC and a moment MC. So if you balance vertically, RC minus 6 over EI minus half times 12 over EI into 3, 0. So RC is 16 plus 6, 18 plus 6, 24 over EI. So what is RC? RC is, what is RC? RC is equal to, RC is equal to shear force. So if RC is a shear force, that is the slope in the real beam. So slope in the real beam is a positive value, right? RC upward. So if you take MC, so MC so MC, if you take counterclockwise, minus MC. So you take moment at C. So minus MC plus half EI 3, and the distance to the centroid is 2. That's also counterclockwise, plus 6 over EI into 3. So MC is 18. Here 2 will cancel out. 36 plus 18 is 54. 54 over EI. Now, what is this correct sign convention? Normally, we mark lagging coefficient. but this one is okay. So it should be minus 54 over here. Okay, it should be minus 54 over. Same thing with the RC. RC is the reaction. Shear will be negative. Okay? Because shear, when it comes to shear, clockwise we mark downward shear positive. Okay? We mark downward shear positive. So clockwise shear is positive. Counterclockwise moment is positive because we tend to sag it. Here it is hug it. Okay? So that is so the deflection at C is minus 54 over EI. So the bending moment in the conjugate beam is equal to the deflection in the real beam. Okay. So the question is displacement at the end of beam, end C of the beam. We got it, and we need to substitute the value and get the values. So if we substitute E 200 gigapascal, so that is equal to 200 into 10 to the 6 kilonewton per meter squared. I is 70 into 10 to the 6 millimeter to the 4. So that is 70 into 10 to the minus 6 meter to the 4. So if I substitute the values, minus 54, G is 200 into 10 to the 6, plus I is 70 into 10 to the minus 6. So it is 54 over 0.00386 meter. 20, right? Not 30. So that is 3.86 millimeter downward. The deflection is downward. Okay, 3 point. So the conjugate beam method is very convenient method to determine slope and deflection at any point in a beam. What you have to do is you have to first determine the support reactions, plot bending moment diagram. So the steps are determine external reactions. 2. Plot bending moment diagram and M over EI diagram. 3. Construct conjugate beam and apply M over EI as load. Then you can derive shear force and bending moment to this new conjugate beam, and the bending moment is equal to the deflection, shear force is equal to the slope at any point. So that is how we do this conjugate beam method. There are problems even in the slides I will upload. There are 1 or 2 problems, but in the book there are problems. So you practice and exercise and familiarize with the method. You can expect a question either in the conjugate beam or in moment area method. So be familiarized with it. And there will be a quiz on Friday. You can do online and upload on either on conjugate beam or on moment area method. Okay, so practice and then do the quiz. So we are going to stop now, and when we come back next week, so we'll start with slope deflection method. This is also another method, but this method is for statically indeterminate structures. So there are 2 methods. Slope deflection is one method. Then moment distribution method. We'll be studying these 2 methods that can be used to analyze any beam that is statically indeterminate. So at the end of this course, you can analyze any beam, whether it's determinate or indeterminate, find moments, find shear force, and calculate deflection. So everything possibly required for designing a simple house would have been covered by this semester in terms of analysis. Then you have to design using what you learn in the next semester. Okay, so we'll stop here and I'll meet you again next Monday.